Hi everybody and welcome to a new video in the audio processing for machine learning series. This time we're basically starting the whole series and it's going to be quite theoretical because I want to introduce a few basic ideas. So what's sound? What are waveforms? And so what's frequency and how can we use all of those notions in audio processing? Okay, so let's get started with the basic idea here. So what is sound? Well, sound is produced by vibrating objects. So these objects vibrate and these vibrations cause our air molecules to oscillate and to bump into each other. And by bumping into each other, these air molecules kind of like change the state of the air pressure in like the local region where they are acting. And so they create in this process a wave. So in other words, we can think of sound as a wave that transfers some energy from one point to another through air molecules. Okay, but the question is, what is a mechanical wave? And I'm talking about mechanical waves here because sound is a mechanical wave. So a mechanical wave is a wave that oscillates and that an oscillation that travels through space. And the energy travels from, as I said, one point to another. And the particularity of mechanical waves is that they need a medium through which the wave can expand and propagate through. In the case of sound, most of the time this medium is just air, right? And when we have this sound wave or a mechanical wave, the medium gets deformed. And in the case of sound, what happens is, like as I mentioned before, is that like this molecules tend to bump into each other, and when that happens we have like higher points of pressure, right? And then when they just like kind of like move away from each other, we have like points of more like rarefaction, of less air pressure. And obviously we can visualize all of this by using a pressure plot, okay? So, but obviously this is not the type of pressure that I want to talk about here, is like air pressure, right? Okay, so basically the idea here is like we can visualize a sound wave as a, in this case, like as a simple like sine wave, right? And so we have at the center here the average atmospheric pressure, and then we have over time points of compression which are connected with this like denser points where like air molecules collide with each other, and then we have like these points of rarefaction where just the air molecules are more spaced out, right? So this is like the whole idea of a sound wave that just kind of like travels through space using air as a medium. Okay, so now we can represent a complex sound using a waveform, which once again is basically like a pressure plot. So we are plotting the deviation of air from this air pressure from this zero level against time. And so with a waveform like this that I'm sure like you'll be familiar with, we can just like represent a whole piece of music, some noise, whatever we want really. And it's a nice way of visualizing and having like a quick understanding and visualization of what like a sound like looks like, okay? And as we'll see, the waveform is going to be like fundamental for doing certain transformations which are going to be very important to get important features about audio signals. Okay, so now a waveform is great because it provides us with an array of different information. It's not just about like frequency information, but also about intensity, timbre, other types of temporal information, duration. So for example, if we have like a complex waveform for like a piece of music, we can identify onsets and the duration of the notes and all of these kind of cues. And it's kind of like mesmerizing that all of that comes from like a very simple graph, a 2D graph. Cool. Okay, so now we can divide sound into a couple of like classes or categories. So we have periodic and aperiodic sound. So in the case of periodic sound, this is like a sound where the compressions and rarefactions repeat regularly, right? So you can fix a period at which you have peaks or you have dips. Now, the simplest form of periodic sound is a single sine wave. And so we know like the math behind sine waves like really well. So that is like very convenient for us. Now, a more complex type of sound, that is like the sound, for example, of an orchestra playing, is the so-called complex sound that, as we'll see in a few videos, is the result of multiple sine waves that get kind of like combined and superimposed together. Now, so this is the type of like periodic sound. Then we have aperiodic sound. Obviously, like the name here is a clear hint. So with aperiodic sound, we don't have like periodicity in the audio signal. And we can differentiate between two types of aperiodic sounds, so continuous and transient. So continuous aperiodic sound is just noise. And basically, you have like a jumble of points as a waveform, which don't follow any pattern whatsoever in the air pressure. It's just like some random points sampled through like the on the air pressure axis. Okay, so the transient aperiodic sound is a little bit different. So all of those like popping sounds or like clicks and things like that can be thought of like as transient. So these are just like bursts of energy and which change like the air pressure suddenly. It's kind of like a pulse thing. And then again, there you don't have any type of periodicity whatsoever. Okay, so now let's try to start with the simplest things first, which is like having like a simple sine wave, okay? So here we have the waveform for like a simple sine wave. And here also down here we have the math for that. And as you can see, we can easily create the equation of this sine wave by using a bunch of like different parameters. So this capital A here is the amplitude, and then we have F, which is the frequency, T is just time, and then phi is the phase. Now let's try to take a look at each of these parameters in isolation so that you get an idea of like how they influence the waveform itself. Okay, so frequency is connected with the idea of period. So the period is very simple like to understand as a concept, right? It's just like the amount of time that we need to elapse before having two peaks or, for example, two dips, right? Okay, so this is the period. Now, the frequency is just the inverse of the period, where we've indicated period with capital T here. And frequency is expressed in hertz, which is number of cycles per second. Okay, so now the amplitude instead is a quite simple, intuitive concept as well to understand. And it's basically how high or low this perturbation in air pressure goes. The higher it goes, and the higher the amplitude, obviously, right? So this is like, we can take like this information just by starting from 0 and then looking at the difference, for example, between the peak, the value of the amplitude at the peak and at 0, right? And so there we have the amplitude. Okay, then the final parameter that we were kind of like pondering was a phase, which is indicated with the phi letter from the Greek alphabet. Okay, so phase, what phase tells us is basically like it enables us like to shift the waveform to the right or to the left, and phase basically tells us what is the position of the waveform at time 0, right? Okay, so with amplitude, with frequency, and with phase, we are able of determining all the parameters and have like a complete understanding of a sine wave. And as we'll see in future videos, this is extremely important because complex sounds can just be thought of as a combination or superimposition of many sine waves together. Okay, cool. Okay, now let's take a look at frequency and amplitude a little bit more. And so as you can see here, we have like here with this red graph, like two waves. And so the one above here has like this frequency, or like, well, that actually like is the period, right? And this one down here has this period here, which is like shorter. So the frequency being the inverse is higher. So what's the relationship between frequency and sound? Well, the higher the frequency, the higher the sound that we perceive, right? Now, a similar thing can happen with amplitude. So we see here with this purple graph in the top right, where the amplitude is quite low. And then down here, bottom right, we have a sine wave with a higher amplitude. And that perceptually translates to have a louder sound. So larger amplitude are connected with louder sounds, and this like makes sense intuitively, because the amplitude just measures the amount of perturbation that happens in the air pressure, right? And the higher the perturbation, the higher the energy that we transfer, and the louder that will sound. Okay, so now here we have like a basic understanding of how frequency and amplitude map onto like perceptual aspects. Okay, so now an interesting thing that I want to cover here is the hearing range. And as we'll see, this is extremely important for decisions in audio processing, like sample rate and a bunch of other things. Now, different animals usually have like very different hearing ranges. So humans, for example, have a hearing range which is between 20 hertz and 20,000 hertz. But if we go and we take a look at the hearing range for cats and dogs, we see that they are capable of hearing also higher frequencies. The frequencies that we humans call ultrasounds, just because like everything is anthropocentric, and so what we can hear and goes beyond like what the highest frequency we can hear is called ultrasounds. And basically like both cats and dogs, and definitely bats, can hear ultrasounds. Right, so now let's take a look at a few examples of like sounds and where they are mapped into the hearing range. So if we take a look at the concert orchestra, for example, in the middle here, so you'll see that the concert orchestra more or less like covers the whole spectrum of hearing range, of human hearing range, and that like makes sense. And so here you have, for example, like the male singing voice, which is between somewhere, I'd say like 60 to 2,000, even like 5,000, and then the female speaking voice, which is usually like an octave above the male speaking voice as a rule of thumb. And so it starts around like 200 hertz and it goes all the way up to 10,000 hertz. Okay, so here like you get an idea of different types of sounds and how they mapped onto hertz and our hearing range. Okay, so now what we've talked about up until now is a kind of objective measure of sound, which is frequency. Now, the way we hear frequency and we perceive frequency is kind of like very subjective, and it's not really like that objective like at all. And now pitch is the concept that we use for the perception of frequency, right? Okay, so the great thing, the interesting thing I should say, like about pitch, is that we don't hear pitch in a we don't hear, I should say, frequency in a linear way, but rather in a logarithmic way. So one other like interesting thing here is that two frequencies are perceived to be more or less like the same if they differ by a power of 2. And so this is like the concept of octave that's coming into place, and we'll cover this. But for now, I want you to understand that the way we perceive pitch or the way we perceive frequency through pitch is kind of like very different from like frequency itself, because we have this kind of like logarithmic perception of frequency. Okay, so to understand the concept of pitch, we need to understand the concept of MIDI notes. Now, MIDI notes are kind of like very common and very handy convention for just like transferring information about like musical notes and stuff like that. But what we want to understand here is that how they map onto like pitch and a keyboard. So now here we have like a piano keyboard, right? And the idea of MIDI notes is that we can attach to each keyboard a number, a MIDI number, right? So for example, the middle C down here has a MIDI note which is equal to 60. Now, we can map these MIDI notes to note names. So this MIDI note 60 is equal to C4. Now, what does that stand for? So we have like for a note name like two parameters there. So one is a letter, and yeah, that's just like the note names, right? C, D, E, F, F sharp, all these things, right? And the other one is a number. So what's that number? Well, that number represents the octave we are at. So now, I guess like most of you are familiar with the concept of like a scale, like or an octave, and you've like perhaps like played around like with a keyboard, like a piano yourself. But if you're not, the basic idea is that we have a pattern of notes that always repeats itself. So we start like with C, we go to C sharp, D, and then E, F, G, A, B, and then we can go up an octave. And here we have like the very same pattern, the very same 12 notes, which we call semitones. So there are like 12 semitones in the whole octave. Okay, so now what's the difference between this, and this? Well, basically like the notes that get like the same name, so C, will sound basically the same, but they'll sound somehow like higher. So it's difficult to explain, but basically like the tone itself is the same, but it will be perceived as higher, okay? So, and basically like with the number here in the note name, like they see 4, the 4 just expresses the octave we are at. And obviously the octave like is this interval that we have like between, for example, like C4 and C5, okay? Cool. So how does that map onto the idea of frequency? So let's take a look at that. So we start with a simple note, a fundamental note, which is A4 or pitch or MIDI note 69. And this is set at 440 Hertz. Now, the idea is that if we go up an octave, so to A5, we'll have the frequency that's double that. It's 880 Hertz. So the basic takeaway point here is that when you have like notes that are like at an octave above, they'll have a frequency that's double the frequency of the same note at the octave below, right? Okay, so now if we take all of these ideas and we plot them on a pitch frequency chart, you'll see that now the connection, like the mapping between frequency and pitch is a logarithmic one. And you can see like here the nice logarithm function here. And here on the y-axis, on the pitch axis, we just have like A0, A1, A2, A3, A4, so on and so forth. And you'll see that basically like at every octave we go above, we just like double the frequency in Hertz down here. Okay, So this is like a very interesting aspect, and it seems that in sound, like the way we perceive sound across the board, not just like for frequency, but also, for example, for amplitude, for like intensity, is a logarithmic. And not only that, but if we're talking about music, even like the very concept of time and rhythm is somehow logarithmic and based on powers of 2. Okay, but yeah, I guess we'll look into that in the coming videos. Okay, so how do we map pitch onto frequency? Here we can use a very simple equation. So you have like this frequency f as a function of p, which is the pitch, and we'll pass the pitch in as a Midi note. And here you have this nice function. So you have 2 to the power of p minus 69 divided by 12. And all of this guy is multiplied by 440. And this 440, you can recognize that's just the frequency at pitch 69 at Midi note 69, because like if you plug into this p here 69, the whole thing here will become 1, and if you multiply that by 440, basically you just get 440, which is the frequency for pitch 69, or A4. Okay, so now let's try to plug like an example number here. Okay, so here we're plugging 60, which is middle C, or I think it's C4, right? And we plug it in here, and when it's all said and done, we get back 261.6, and that's the frequency for pitch 60. Now, so as we said, an octave is divided into 12 semitones, okay? So 12 different notes that are that have like the same distance, like among themselves, right? Okay, so they basically divide the whole octave in 12 equal parts. Okay, so so what's the relationship between two subsequent pitches? Okay, and so we can just like take a look at that by using like this function, this equation here. So the frequency of p plus 1, which is like the subsequent pitch to the one that we are analyzing, so the subsequent semitone, divided by fp, the ratio is given by 2 to the power of 1 divided by 12, okay? And that's equal to 1.059. So this is like the ratio between two subsequent semitones, and this remains always the same throughout like the entire like keyboard of a piano, if you will. Okay, so now one thing that I want you to notice here is that like this is like quite intuitive, and it's because so basically we're saying that like every time we go up an octave, like this factor is going to be like equal to 2, like the factor, like the multiplication factor of the frequency is going to be equal to 2. But if we go just up a semitone, so this is going to be equal to 2 to the power of 1 divided by 12, because we know that we are dividing the octave in 12 semitones. Okay, cool. Okay, so now to finish this video, I want to talk about sense. So this is like another very important concept, and it's related with the idea of like music perception mainly. So the idea is basically that we have like a quite decent resolution when it comes time to pitch. Obviously, we are capable of like picking up like different semitones and understanding that there's a difference in pitch there, but we are better than that. So we are capable of like appreciating pitch differences that are smaller than a semitone. So how can we measure that? Well, here is where cents come into place. So the idea of a cent is that the whole octave is divided in 1200 cents. So we have 100 cents for each semitone. Okay, and so here the cool thing is that obviously like there's a threshold below which we can't just like really tell the difference between two pitches. But that threshold of so-called noticeable pitch difference is between 10 and 25 cents, depending like on who you are, I guess your age and your background, if you are like a musician or you're not. Probably if you're a musician, like you are capable of appreciating pitch differences way better than non-musicians. Okay, cool. So by now you should have like a fair understanding of what sound is, what a waveform is, and everything that has to do with frequency and pitch. So the next time we'll continue delving into sound and all the different parameters which actually describe sound. Precisely, we're going to talk about intensity, power, and loudness, that are all features that are somehow correlated or connected with the idea of amplitude. And then we'll also venture into a very cool topic, which is that of timbre, the timbre of sound. And this is like a very difficult one like to grasp, because it's very nuanced and it's very, I don't know, like very ambiguous, I would say, and subjective. Okay, so I hope you enjoyed this video. If that's the case, please remember to leave a like, and if you haven't subscribed to the channel, please do, so you'll get like all the videos that I'm posting. And finally, I want to remember that we have a community which is on a Slack workspace that's called The Sound of AI, where if you join, you're going to be able to just like join the discussion, ask questions with the community, get feedback, and yeah, happen to know like very cool people. Okay, that's all for today. I hope I'll see you next time. Cheers.